All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Hello, welcome to SChand Academy. In the last lecture, we had covered the interference with the wedge-shaped film, and we could be able to relate and connect to the last lecture to this lecture. We are going to study the Newton rings, and to study the Newton rings, we could be able to understand interference observed in the thin films as well as in the wedge-shaped film. So, to understanding of the Newton rings, we could be able to know the refractive index of the liquid, of the medium. If you want to go more in detail about it, you can see the name of the book which is coming at the lower side of the screen, where you can go through with that book and can have detailed discussion of those topics which we are covering in the class. We had covered in the last lecture the interference in the thin films. The thin films, uniform thin film as well as the wedge-shaped thin film. So, when we talked of the normal thin film which is having a uniform thickness, we could be able to see what exactly the path difference between the two rays which are coming from reflection and refraction, which is the division of amplitude. So, we discussed two type of interferences, where we are getting one is with the division of wavefront and second is division of amplitude, and we covered that what will be the path difference for the two rays which are coming from a single source, how is going to implement it in the case of Newton rings. Where we stopped last time, or we discussed that there will be a path difference between the two rays, the reflected ray and the ray which is coming through that particular film. And where we stopped, we could be able to see that the path difference between the two is 2 mu t cos r plus theta minus lambda by 2. So, for getting the constructive and destructive interferences, there is a condition which is, you can see onto the screen, 2 mu t cos r plus theta minus lambda by 2 is equal to 2m lambda by 2 for observing the constructive interference, where m is equal to 0, 1, 2 and 3. So, if you see 2 mu t cos r plus theta is equal to 2m plus 1 lambda by 2, where m is equal to 0, 1, 2 and 3, it means when we are putting the values of m is equal to 0, 1, 2 and 3, we could be able to see the different type of constructive interference, so on. It means, as we know in the constructive interferences or interference specifically, that we get constructive and destructive interferences on a regular interval of time, and there is a systematic pattern, we are observing it. Now, when we say there is a destructive interference, at that time 2 mu t cos r plus theta is equal to 2n minus 1 lambda by 2, which is the condition. So, you see 2 mu t cos r is equal to n lambda and n is equal to 0, 1, 2 and 3. So, these are the two conditions required for observing the destructive and constructive interferences when we are considering a wedge-shaped film. Now, up to now we could be able to have a better understanding of the interference observed in the thin films. Now, we will just specifically understand what exactly in the Newton rings the things happens. What is the construction of the Newton rings, what type of experimental arrangement is there for the Newton rings, and how do we implement the system for observing the refractive index of any medium with the help of Newton rings, and can we observe the wavelength of the light which is being used in the case of Newton rings. As I said it, for observing the interference pattern, we need to have a monochromatic source. So, if we are not knowing what type of monochromatic source is being used in the experiment of Newton rings, With the help of Newton rings also we could be able to know what is the wavelength of that particular source we are using. So this is one of the applications. There are two applications of the Newton rings, and then we can relate it to the practical life. The important is that we could be able to know the source, whether it's a monochromatic, dichromatic, polychromatic, we need to see, because for interference pattern we need to observe. If we need to see, it should be a monochromatic source. And the second is we could be able to know the refractive index of that particular liquid. Now we'll just specifically come on to the arrangement which is in the Newton rings is happening. You see, if we go to the next slide, we can see there is a source, right, and we are just discussing what type of arrangement normally we have in the case of Newton rings. And what we are discussing right now, we are discussing Newton rings in the reflected light, right, because there is a possibility of Newton rings observed in the transmitted light also, but right now first we will be discussing for the reflected light. So what is the arrangement? There is a light source is there, source is, because source is there, source is it is coming, the rays are coming in all the directions. We have just using a lens, as you can see onto the screen, lens L1 is being used, that is put at the locus, right. So light rays emitting from S, they are impinging onto the lens L1, getting parallel to it, and there is a glass plate which is inclined at 45 degree. We are mentioning in the figure at plate G, right, and then because it is inclined at 45 degrees, so rays coming from a source after becoming parallel to the lens, it is impinging onto the plate, glass plate which is inclined at 45 degree. Part of it is getting reflected in the direction, lower direction, where we had kept an arrangement. That arrangement is the plane glass plate which is mentioning as E, and there is a plano-convex lens, right. What is a plano-convex lens? The plano-convex, as it is clear from its name, the one surface is plane, the other surface is convex, right. So why we have done so and how it is related with the wedge-shaped film, we are just understanding it, because when you are putting the plane glass plate, right, and you are going to put it like this, or we can, if I say specifically like this or like this, see. So this is a glass plate, and if I put my hand like this, so when we are discussing that where exactly the wedge-shaped film is there in this case, so we can see this is a plane glass plate, right. Suppose we are mentioning it as E, and plano-convex lens, this is an arrangement, you see, this is a plano-convex, the convex side is touching, suppose the point of contact between the plane glass plate and the plano-convex side is this. So it means the point of contact means the convex side is touching the plane glass plate. So now you will see, if you see this one like this, now this is exactly the wedge-shaped film we are talking earlier. Why so? Because at point of contact, we discussed it when OP and OQ we had discussed it. They are the two surfaces where their point of contact, the thickness is 0. Similarly, it is happening at this point of contact O, where convex side is touching the glass plate, and when we are going away from point O, the thickness is increasing. So this is a wedge-shaped film. Now this is an arrangement at the lower side. Now we'll just come back to the clear picture which we are having it. There was a light source which is a monochromatic source. The light is coming from that particular source. We had made a lens. Lens is making the rays parallel, and there is a glass plate which is inclined at 45 degree. You all can see onto the screen, and it is coming onto the glass plate which is mentioning at G. When they are inclined on this one, they are coming back to the arrangement, the plano-convex lens and the plane glass plate, right. And then after then wedge-shaped film which we had discussed it, what is happening inside it, again that phenomenon is happening here, and then while reflecting back, it is again passing through from this one, and there is M, which is a microscope is mentioned, and we could be able to see something we are going to observe. Now it means what is there? There are 5 things involved in the process. One is the source, second is the lens, third is the glass plate, fourth is the plano-convex lens and the plane glass plate arrangement, which is working as a wedge-shaped film, and the microscope. So this is the experimental arrangement for the Newton rings in the reflected light. Now the phenomenon of Newton rings was satisfactorily explained by Young's. So what exactly he said it, that because we are using a convex side of it, so at a point of contact, the locus of all the points corresponding to the specific thickness of the air film falls on the circle at a point of contact O. Therefore we are observing the rings. I repeat it, the locus of all the points to the specific thin film at a different point comes to the point of contact O. The locus of all the points specific to the thickness of all the films lies at point of contact O. Therefore we observe the rings as circular rings. This is very important. Now it means what is happening, that we are getting a point of contact, there is a dark spot, and as you can see there is a point of contact, like we will getting a dark spot, and we will be getting like this type of rings are being observed. So because it was observed by Newton, that's why it is called Newton rings, right? But we need to understand it, that how it is happening, what phenomenon is happening, as we discussed in the case. So we'll discuss one by one. I'll try to understand it, that how the constructive and destructive interference will be observed in the case of Newton rings, and how do we observe, can we observe the diameter of the rings in case of dark rings or the bright rings which we are observing, right? So this is the one thing, right? Now if I'll just make a graph picture again. This is a glass plate, we had made it. This is a planar convex lens, we had made it. Now you see, if I made a source here and light is incident on it, right, and suppose we are saying it, so it is again it is getting reflected in that way, again it is coming here, and then we are observing the light. So it means it is something is happening here, as we know that. If you all can see onto the screen, light is coming from source S, right, and then there is a point of contact, we are saying, right. So I have made already it in the previous figure, that there is a wedge-shaped film, and all the things happening in the wedge-shaped film in the same way as we discussed in the last class or in the last figure which we had discussed it. So you see, and then we say this is ray 1, this is ray 2, this is ray 1, this is ray 2. So it means, and then if we put a lens over here, we will be able to observe the interference pattern between the two rays. You see, so it means from a single source we are getting the two light source 1 and 2. So those are coherent, and we will be able to observe the interference pattern. Now so 1 or 2 rays are the reflected and interfering rays corresponding to the incident ray SP, right. So effective path difference between the interfering rays in the reflected light we had calculated earlier, which was equal to 2 mu t cos r plus theta minus lambda by 2. This is in the previous section which we had covered it, 2 mu t cos r plus theta minus lambda by 2. And what was v? Mu is the refractive index, right? T is the thickness of the film, and r is the angle of refraction, and the theta is the angle of wedge shaped film, right? So theta is the angle of wedge, r angle of refraction, T is the thickness, and the path difference is 2 mu t cos r plus theta minus lambda by 2. Now these are the things which we observed it, and now one thing we need to see, when r is equal to 0, what is going to happen? When incidence is normal, and r is equal to 0, the angle of wedge, suppose we are considering, is very small. Two things we need to observe now. When r is equal to 0, it means we are putting the incidence as a normal incidence. When normal incidence is there, and in a wedge shaped film, suppose the theta, angle theta, here in this case this theta, as we normally know it in the case of theta, if it is very small, so cos r plus theta, what is going to happen? Cos r plus theta is equal to cos of r plus theta is equal to cos r, we said it for normal incidence 0, so it is equal to cos theta. So cos theta is equal to 1. For normal incidence, if we are saying an angle of refraction theta is very small, cos theta is equal to 1. So the effective path difference will be equal to the effective path. So it means this cos r plus theta will become cos theta, right? So it will be equal to 2 mu t, and cos theta, for normal incidence we are considering it, maximum value is 1. So this cos theta is equal to 1, it will be equal to 2 mu t minus lambda by 2. So this is the effective part difference. Delta is equal to 2 mu t minus lambda by 2. So it means point of contact kya hai? There, what is the point of contact? Point of contact is point O on the lens and plate T is equal to 0. See, so at the point of contact when plano convex lens and plane glass plate are touching each other, at that particular point of time thickness is 0, right? And incidence is normal, we know that. And so therefore lambda आपका कितना हो गया? This is equal to lambda by 2, right? So this is this is the condition of minimum intensity, right? So when t is equal to, why we are saying so? Because we have considered t is equal to 0. As we consider t is equal to 0 to 2 mu t minus lambda by 2, which is the effective part difference we had calculated, but at the point of contact between plano convex lens and plane glass plate t is equal to 0. So at that point we can say that the delta is equal to lambda by. So this is a condition of minimum intensity. That's why I said it. So central spot of the rings is dark. You see, this is the point. As I made it in the earlier figure, the rings we have made it, and I said it at the point of contact the central spot will be dark. So why we are getting a dark spot? Because there is a minimum intensity. And why we got a minimum intensity? Because the part difference comes out to be 2 mu t minus lambda by 2, but thickness is 0. Therefore we will be getting delta is equal to lambda by 2, which is a condition for the minimum intensity. So it means the central spot will be dark. Now as I said it earlier also, that we are getting dark spot and then we are getting concentric rings. I said it, I repeat it again. We are getting the concentric rings and the central spot is dark, and we are getting alternatively dark, bright, dark, bright, dark, bright fringes. It means, and we are getting circular also. Circular we got it. One reason is for getting circular is the locus of all the points specific to the thickness of the film falls on the circle at a point of contact O. This is the one reason we are getting, and then we are getting, because it is the division of amplitude, so we are getting interference due to the division of amplitude, and it is a characteristic property of the interference that we get regular interval of time, the dark or constructive, dark or bright, or constructive or destructive interferences. That's why we are getting the circular rings. So you see, now up to now what we had studied that when we are observing the rings with the help of the wedge-shaped film, we are getting the alternatively bright and dark fringes. Those are circular. And why we are getting the center spot as dark? Because we are getting the minimum intensity and we are getting destructive interference, and point of contact because of the thickness is equal to 0, and we had considered the theta is very small, so therefore we will be getting the minimum intensity. Now when we will move further, when we will move to the next section, surely we will be studying that what is the condition for maxima, right? So when we have to study, so in the next section we will be studying about the condition for observing the maxima.
Hi, I am Manisha Singla. मैं इनऑर्गेनिक के कुछ कॉन्सेप्ट्स जैसे कि बॉन्डिंग है, आयनिक, कोवलेंट, एटॉमिक स्ट्रक्चर है, उनके प्रिंसिपल्स हैं, थियोरीज हैं, उनको थोड़ा इजी मैनर में SChand अकेडमी में बताऊंगी. तो अगर आप मेरे साथ पढ़ना चाहते हैं तो सब्सक्राइब ज़रूर कीजिए.
So welcome to the SChand Academy. In the last lecture we had covered the condition which is required for observing the minimum intensity in the wedge-shaped film, and we were discussing about the Newton rings. We could be able to know that why the rings are circular, right? We could be able to know that why the center spot is dark, and that condition we had observed, that is the condition for observing the minimum intensity, and that was delta is equal to lambda by 2, right? So center spot of the rings are dark. Now the condition for maximum intensity or for a bright ring is equal to 2 mu t minus lambda by 2 is equal to 2m lambda by 2. Now 2 mu t and Now 2 mu t minus lambda by 2 is equal to 2m lambda upon 2. Now where m is equal to, we know that m is equal to 0, 1 and 2. Now when we are saying this, it means we can calculate the value of 2 mu t, which comes out to be 2m plus 1 lambda by 2. So this is the condition for observing the maximum intensity. Now the 2 mu t is equal to, now we say, if we say 2 mu t is equal to 2n minus 1 lambda upon 2, where n is equal to 0, 1, 2 and 3 and so on, at that particular point of time, the condition for maximum intensity, that is for the dark ring, that is for a dark ring. So what we are observing it, that we are trying to find it out, that what is the condition for observing the maximum and minimum intensities, which will help us to have an understanding that where we are getting the dark spot, where we are getting the bright spot, right? And we discussed it that we will be getting the concentric rings, and because of this reason, why? Because the locus of all the points corresponding to the specific thickness of the film falls on the circle at point O, which is the point of contact, right? So this is important, that we are getting the concentric rings, center spot dark, and then we are getting bright dark, and this is the significance of the interference, that we get normally the constructive and destructive interferences, right? So if we move further, we can calculate the diameter of the dark and the bright rings as well. So if we see onto the screen, we have made just a geometry is there. We can calculate that what will be the radii of the dark and the bright rings. So as you see it, there is a point of contact O. We had made the thickness as small t. So and we have made the plano-convex lens as well. So if we see this one, plano-convex lens is there and it is placed at a glass plate R, and then we said the point of contact is T, point of contact is O, I'm sorry, and then R with the radius of that curved surface, the lens, and T is the thickness of the film, right, at the point P, right. So from the property of the circle, we know that AP into PB, AP into AB is equal to OA into AF, right. So AP and AB are the radii, radius of the ring that is passing through that P. OA and PH is equal to, as we can say, it is T. You can see here. When we solve it, we can calculate the value of small t, which is coming out to be r square upon 2r. Now r is, small r is different, capital R is different, and as you can see this one, OA we are mentioning, PH we are mentioning, which is the thickness of that wedge shaped film, but r is the radius of curvature and small r is the radii of the ring passing through that particular P. So this is the difference, but we know that radius of curvature is too much. That's why to observe the rings in the Newton rings experiment, the radius of curvature should be very large. If we do that, we'll be able to observe the rings in the better way, right. So and t is equal to, we got it, this is r square, small r square upon 2r, right. So it means for the bright rings, if we are saying it, so we can calculate it for the bright rings, 2 mu t cos r as we normally note it. So 2 mu and this is r square upon 2r is equal to 2n minus 1 lambda upon 2. This is a condition which you can see on the previous slides, which we had known it. So 2 mu t cos r, t we can write the value t, r square upon 2r is equal to 2n minus 1 lambda upon 2. We have put the value of small t in that equation, where 2 mu t cos r is equal to 2n minus 1 lambda upon 2, which was a condition for observing the bright rings. So if we calculate the value of r, we can calculate it that the radius of the nth ring we can calculate it, and which is coming out to be, if you can write it, rn square we can calculate it, it is 2n minus 1 lambda r upon 2 mu. This is if we are going to put the value of T in that equation for observing the bright ring, right? So Rn is, I have kept it Rn, and we kept it for nth ring we are talking of, or nth bright ring we are talking of. So we'll be getting this one, and if capital Dn, suppose we consider Dn is the diameter of the nth bright ring, so Rn will be equal to Dn upon 2. Rn will be equal to Dn upon 2. So we can calculate the Dn square. So Dn upon 2 square, we can calculate it, is equal to 2n minus 1 lambda r upon 2 mu, right? So you see, so it means we can calculate what will be Dn square. Dn square we can calculate it. It comes out to be 2 into 2n minus 1. This is lambda r upon mu, right? So it means for the air film, what we are saying, for the air film mu is equal to 1. When mu is equal to 1, what will be Dn square? Dn square will be equal to 2 into 2n minus 1 into lambda r, right? So Dn square is equal to 2 into 2n minus 1 into r. So if we can calculate the value of Dn also, Dn will be equal to under root of this 2 of 2n minus 1 into lambda into r. You see, so it means when we are talking of the radii of the nth bright ring, it is dependent on what? It is dependent on, if you see this equation, Dn is equal to under root 2 lambda r under root 2n minus 1. So if I ask a question from all of you that what is the factor which is responsible for observing the diameter of the bright ring, we can surely tell us that it is depending on what? Lambda r is the radius of curvature, obviously, and n is the number of, we know that it is n is equal to 0, 1, 2, it's an integer, no problem. So lambda is there, the wavelength is there, so Dn is dependent on these particular things. So lambda r and 2n minus 1. Dn comes out to be, Dn is equal to, we can say Dn is equal to k into, so we can write it as Dn is equal to k of under root 2n minus 1, right? So as we can see this one, n is equal to 1, 2, 3 up to 2n minus 1 is an odd number, right? So diameter, what exactly the conclusion we had drawn, that the diameter of the dark rings are proportional to the square root of the natural number. You see, it is very important. This is what the conclusion we had drawn, that the diameter of the bright rings are proportional to the square root of those natural numbers. Similarly, we can do it for the dark rings also. So dark rings, you can clear it 2 mu. Again, we are going to put the value in the earlier equation which is responsible for the dark rings as we did it for the bright rings. So 2 mu r square upon 2r is equal to n lambda, right? I hope it is clear to each and every one of you. And then we are going to calculate r. R will be equal to, the value comes out to be n lambda r upon mu. So r is equal to n lambda r upon mu. Similarly, so we can calculate the Dn for this also. Dn comes out to be k into under root n. If we solve this, we could be able to know diameter. We said it, diameter is equal to again the twice of the radii, and when we calculate the value of Dn, it comes out to be k under root n, right? So what diameter of the successive dark rings is proportional to the square root of the natural numbers. See, the two conclusions we had drawn right now based on the conditions required for observing the bright and the dark rings or constructive and destructive interferences. So we'll be studying in the next section about that, because we did it for the reflected light. Do we observe the same type of thing for transmitted light also, and at what time the diameter depends on which factors we'll be studying in the next section. Thank you. So this is the end of part of it. If you want to go more in detail about the topics, I can recommend the textbook of engineering physics by Professor Avdhanulu, which is coming onto the screen, and you can go in detail about these subjects with this book. I hope you must have enjoyed it. Please like, share and subscribe.